Hello everyone. In this video, we plan to talk about how to use Google Cloud to build infrastructure for your website that is scalable, highly available, and widely distributed. Today's presentation has two parts. The first provides a high-level overview of what infrastructure pieces are involved and how they fit with each other. As a brief introduction, I'm Karthik, a product manager within Google Cloud. The second part walks you through the details of how to use gCloud to actually build the infrastructure end to end and will be covered by my colleague Armand Rai. While there are many options available, the key insight we want to drive is to showcase how Google Cloud can be used as a one stop shop for building scalable, highly available websites that can be distributed all across the globe with relatively low effort. Here are the products that we will cover in this video. Let's start at the very beginning, buying and registering a domain. Until now, this process was outside Google Cloud and it was not very straightforward to buy, register, verify the ownership, and set up DNS records so that your customers can reach your website. We have recently launched Google Domains that is integrated into Google Cloud to offer a more seamless workflow and to manage your domain's lifecycle. Cloud Domains allows you to check for availability of the domain name and purchase it. It will also register this domain and verify the ownership. Finally, it supports APIs so you can programmatically manage your domain portfolio. Once domain has been registered, the next step is to create DNS records so your customers can visit your website. Cloud DNS offers public DNS zones that are accessible worldwide and has high availability and scalability. We will create a public DNS zone for the new domain you've just registered in this step. Cloud DNS also supports DNSSEC, and enabling it is very easy. DNSSEC is used to defend against techniques that hackers use to direct computers to rogue websites and servers. We will need to add DNS records to this zone before it's reachable by your customers, but we will do that in a different step. As next steps, we will create the backends. This represents the actual web server that runs your website. We will split this into two parts. Use managed instance group for serving your website. This represents compute virtual machines that process incoming requests and identify what actions to take. We use managed instance groups primarily because you can control them as a single entity and because it is easy to scale when the demand for your website increases, say during a holiday season. Managed instance groups work by using a template that you create. The template defines machine type, boot disk image, or container image and other instance properties. Once created, you can either create individual VMs or groups of VMs and control them as a single entity. You can manually set the size of the number of VMs or use auto scaling if your website is stateless. The managed instance group automatic updater also lets you safely deploy new versions of software to your MIG and supports a flexible range of rollout scenarios, such as rolling updates and canary updates. You can control the speed and scope of deployment as well as the level of disruption to your service. Finally, you can deploy this in multiple GCP regions, increasing your fault tolerance and availability. Next, we use cloud storage for static content like images, backgrounds, videos, and other portions of your website that don't change frequently. Cloud storage allows you to store large quantities of data that can be accessed worldwide. More importantly, it offers high availability with multiple redundancy options. It also makes it easy to ingest your media content on the one end and makes it easy to distribute over a content delivery network like Cloud CDN or another provider. After creating backends, we will create the front end that will handle the traffic to your website. Google Cloud HTTPS load balancing is a global proxy-based layer 7 load balancer that enables you to run and scale your services worldwide behind a single external IP address. It does much better than DNS-based load balancing because there are no TTLs involved and the load balancer can respond much quicker to changes in traffic patterns or health of the backends. It also allows you to do content-based load balancing using URL maps to select the appropriate backend service. Finally, you can run within Google's premium tier networking that will offer cross-regional load balancing and allowing you to direct traffic to the closest healthy backend that has capacity. Now it's time to add some security by adding Cloud Armor to the incoming traffic. Cloud Armor sits at the Google edge and provides DDoS protection along with predefined rules that defend against cross-site scripting and SQL injection attacks. You can also create custom IP-based allow and deny lists and prevent malicious users from consuming your resources. Here's an overall picture that shows how everything is put together. With that, I hand it over to Arman, who will go over the same steps but in much greater detail.
Thanks, Karthik. My name is Arman Rai, and I am a network specialist at Google Cloud. For this portion of the presentation, I will walk you through an example deployment on Google Cloud from start to finish. We will go from ordering a domain all the way through verifying that all the appropriate features are enabled. Let's get started. We will begin our demo with the domain registration process. The first step is to check that the domain you would like to purchase is available. Running the search domains command will give you a list of TLDs and the associated prices. Even though we have specified a .com in the search, the result will give many TLDs that are available for purchase. Once you have decided on the domain name you would like to purchase and confirmed it is available, you need to create a Cloud DNS zone with the domain name. This zone is where you will manage DNS for this domain. Make sure you set the DNSSEC state to on to utilize the security benefits of DNSSEC. Next, you will actually need to order the domain. The gCloud response from the registrar command will prompt you to add information about your business and list a point of contact. The final step is to link the DNS zone that we created in step 1 to the domain cloud domains. This will ensure that the appropriate name server records as well as the appropriate DS records are added for DNSSEC. A great feature of the GCP platform is that this step is automated for you, so you don't need to do it yourself. We strongly encourage customers to use GCP for both their DNS and registrar needs due to these increasing product synergies. In this demo, we will be configuring two backends, one for static content like images, logos, or videos, and the other for dynamic content like HTML and any APIs your website relies on. Let's start with the static content. First, we create a storage bucket. For this bucket, we have chosen to have it be regional in our US East 1 location and to use the standard storage class. Second, we must add some content to the storage bucket. In a typical deployment, there are many options on how to upload content to a storage bucket. Please see our documentation for further information about how to do so. Third, we will update the bucket permissions to public so that anyone can access the content stored. You can additionally leverage IAM permissions if you would like to restrict access to the bucket, but we will not be covering that in this demo. Now that we have set up our static content storage bucket, we will pivot to dynamic traffic. Before we can create a managed instance group, we must create a template which will be the blueprint for all of the compute we will utilize. There's a lot of metadata you can add in this template. In this example, we have picked a region for the compute to be deployed, a VPC network that my networking is utilizing, as well as a specific subnet which I want my compute instances to utilize. We have additionally specified an image for the compute and a simple startup script to install Apache and run a basic web server. Now that we've created the template for our dynamic traffic to use, we need to instantiate the actual instance group. The first command creates the instance group using the template we just created. The second command specifies that we are running our web application on port 80. In this demo, we are using HTTP for the backend of our load balancer since all traffic is on Google's private network. If you'd like, you can additionally run HTTPS traffic on port 443 for your backends. Before we get into creating the load balancer, I want to spend a few moments discussing what are the different components from a gCloud perspective that are required. Starting from the left in this diagram, we need a globally accessible static IP address. This is the IP address that will correspond to our load balancer and is linked using a forwarding rule. Second, we have the actual proxy itself. We need to create two proxies, one for HTTP and one for HTTPS. The global HTTP load balancer is a proxy load balancer, so this step is required. Third, we need to input some logic that defines how traffic is routed between our dynamic backends and our static backends. This configuration is called the URL map. Finally, we need to identify the different backends that we want the traffic to be sent to, one for our static bucket and one for our instance group. In addition, we need to configure whether we'd like to use Cloud CDN for content caching or Cloud Armor for security. There are two steps we need to take before we start configuring the load balancer. We need to reserve a static IP address for our load balancer to use. A common mistake in this step is not to specify the global flag. Once we have reserved it, we need to list it. Please save this IP address for later in the demonstration. It's worth mentioning that as long as this IP address is in your static IP addresses, this IP will be able to be utilized by your resources in your GCP project. Additionally, we need to make sure that the firewall in our VPC is set to allow traffic from the /16 and /22 CIDR ranges listed. If you do not do this step, your health checks will be blocked and no traffic will be able to reach your backend. Now we can get started with configuring our load balancer. In this first command, we create a basic health check, which will probe our backend on port 80. This command utilizes the default settings. Know that there are a lot of customizations available beyond the defaults for health checks, but we will not be covering them in this session. Health checks are a very powerful tool, which allow for only healthy backends to receive end-user traffic. The second command creates a backend service which we will attach to our backends too. You need to attach a health check to the backend service. Once we have created our backend service, we need to add the backends to it. The first command adds our dynamic backend service to the backend. The second command creates a backend bucket for our static content. Additionally, we are including the enable CDN flag in our request. By turning on the CDN, we are ensuring that static content is served globally from Google's edge caches instead of direct from the bucket every time. By doing so, we are greatly increasing the speed of the website. Cloud CDN by default will cache static file types. Google determines file type by looking at the MIME type of the response from origin. We then map the MIME type to a list of static content mappings that we maintain. If you do not want to utilize this method for cache control, no problem. You can set your own cache control headers at origin, or you can configure a force cache all setting. Be careful when setting the force cache all setting because you may inadvertently end up caching content that is intended to be dynamic, i.e. non-cacheable. The third command here adds a custom response header to requests for this backend. The custom response header indicates whether or not the request was served from the CDN cache. There are a lot of other custom headers that can be added in addition to the cache status. You can additionally add your own headers and set them to be whatever you'd like. Once the backends are created, we need to create a URL map. The URL map is a construct that is used to determine traffic routing between our backends. The first command creates the URL map object. In this command, we are specifying that the default location for traffic to be sent to is our dynamic backend. The second command adds the logic that any traffic destined to the path or directory /images/star should instead be sent to the backend bucket. You can add many different paths here, but for our demo, we're just going to use one. Additionally, it's worth mentioning that there are many more advanced routing capabilities available to you beyond path matching in the global HTTPS load balancer. The full list of attributes that you can route on in the URL map is listed in our documentation, as well as guidance on how to deploy this. In this section, we will create the proxies and order an SSL certificate to be served at our edge. The SSL certificate will be issued by Google Certificate Authority, or Let's Encrypt. There are a lot of customizations available within SSL at GCP. You can specify, for example, which TLS versions you would like to support, or what cipher suites you would like clients to support as well. In this example, we're going to stick with the defaults. The first command creates the HTTP proxy. This is linked to the URL map, which we created in the previous step. The second command orders an SSL certificate. There are no validation records we need to add since we are using Cloud DNS. And later, we will point traffic to the static IP assigned to this load balancer. The SSL certificate will take a few minutes to provision, but it will be done automatically. We need to make sure, however, that we specify all of the host names that we want listed here in the certificate. Even while the SSL certificate is provisioning, we can use this SSL certificate to attach to our HTTPS proxy, which is what we are doing in step 3. The last step of the load balancer is to attach the static IP to the HTTP and HTTPS proxies. Step 1 attaches the IP to the HTTP proxy, and step 2 attaches the IP to the HTTPS proxy. By doing this, the IP address, which is announced globally, will be accessible from the internet on both ports 80 and 443. We aren't covering it in this demo, but you can do an HTTP to HTTPS redirect in the load balancer. You can also set HSTS response headers if you would like all future requests by the same client to use HTTPS no matter what. One of the last steps in our demo is to create a Google Cloud Armor policy. Cloud Armor is Google's DDoS and web application firewall solution. Before we configure it, I want to quickly explain how Cloud Armor works and how it is provisioned. Cloud Armor, similar to Cloud CDN, is available as part of the global HTTPS load balancer. Cloud Armor consists of security policies. A security policy is a collection of rules. Rules can be custom firewall rules or particular protections included in the OWASP Top 10. A Cloud Armor rule has a priority associated with it. Similar to the VPC firewall, the lower the priority number, the higher up in the match hierarchy a given rule is. A security policy is attached to a backend service. A backend service can only have one security policy associated with it. A security policy can be reused, however, across multiple backend services. To configure Cloud Armor, we must first create a security policy. The security policy will contain the rules that are applied to our dynamic content backend. Once the security policy has been created, we can then create an example rule. The example rule I created will block any traffic that contains the HTTP request header called evil header. I've also specified that I would like to respond to this traffic with a 403 response code. This custom rule utilizes the Common Expression Language, or CEL. This is an open source language designed for simplicity, speed, safety, and portability. I want to take this moment to additionally highlight that there is an implicit rule in Cloud Armor security policies which dictates whether traffic is allowed or blocked by default for that security policy. If we do not specify this flag in the first command, it will default to an allow setting. This translates to any traffic that does not match any of the rules we configure will be let through. Now that we have a security policy and an example rule, the remaining step is to apply it to a backend. The second step here is an optional one, but a recommended step. It enables Cloud Armor's adaptive protection feature. Adaptive protection builds machine learning models which detect and alert on anomalous application level activity. It additionally generates a signature describing the attack as well as generates a custom Google WAF rule to block the detected signature. Adaptive protection is in public preview as of the time of this recording. It's worth mentioning as well that the custom rule that adaptive protection generates is not automatically applied. There is an alerting mechanism, and you as the user can decide whether or not you want to deploy this rule for your backend. Now that everything is set up, the only task we have left to do is to point DNS to the IP we reserved for our load balancer. Earlier in the presentation, we highlighted how to reserve and obtain this static IP address. If you didn't get a chance to write it down, you can always go back and relist your static IP addresses for your project. The DNS gCloud integration utilizes a concept called a transaction. To add any new records, you must begin a transaction. You can see this command in step 1, where we start a transaction for our zone. Once the transaction has begun, you need to specify the records you would like to add. In this example, since we are only adding 2 records, I've explicitly listed them individually. If you have many records, you can upload your records using a bind file. For this demonstration, we will be adding a www record and an apex record, pointing to the static IP address we configured earlier. Now that we have added the records, we can complete our transaction. Once the transaction completes, the change then propagates to our edge, and traffic will be routable for the www and apex domains. We have completed the setup for our demo. Now, for a final few checks, we can make sure that everything is functioning as it is supposed to. The first check is perhaps the most obvious. I'm able to access the image we uploaded to our storage bucket at the URL listed, www.gcpweb.demo.com/images/snowboarding.jpg. This site is accessible over HTTPS. I've included a screenshot of the certificate information from my browser. No warnings are prompted, and the correct common name is listed. The certificate is valid and has not expired. Additionally, you can see that the organization is Google Trust Services for this particular certificate. Next, we will verify that Cloud CDN is running and that static content is being cached at Google's edge as we expected it to. I've sent a curl to an image in the storage bucket we created, the snowboarding.jpg. In the response, I can see the custom response header we added, gcp-cache-status, with the value hit. This means that the response was served from a GCP edge cache and not from the bucket directly. By using Cloud CDN, you're able to improve origin offload and reduce egress costs, while simultaneously increasing the response speed for the end user. To test that Cloud Armor is working, we can send a curl request, including the header name evil header. We configured the Cloud Armor security policy with a rule that explicitly blocks traffic with this header. The response from the curl is a 403 forbidden, which is exactly what we expected and consistent with what was configured. Thank you for listening to this presentation and demo. We hope you found it useful. Please add your questions to the comments if you have any. Thanks.